All right, so we've started recording. So we're going to start off by talking just about different types of neutralization reactions. And so effectively, it's going to be a combination of, you can kind of already see it on the screen, strong acid, strong base, weak acid, strong base, strong acid, weak base. We'll briefly touch on weak acid, weak base, and then we'll move into titrations. So you might have heard that word before. We'll formally define it later, so don't worry about that. For now, let's just focus on neutralization reactions. The nice way to start off is a reaction that we've been doing since 1101, and you probably saw in high school. It's taking the strong acid, hydrochloric acid, reacting it with sodium hydroxide. I realized this morning, and I haven't had a chance to fix it, that I do have a couple of errors with the arrows, and I'll fix those as we go. The way I would write this is actually unidirectional. The reason for that, and we're going to make ourselves a rule for our class. When we have a neutralization reaction, maybe we should put the whole thing in, neutralization reaction, right? If it's a strong acid or strong base, assume 100% completion. So that means everything to products is what we're looking at. And to make it a little bit more, give ourselves some leeway room, I'll say approximately 100% completion. Because yes, in real life, there is a small reverse reaction, but just like when we were looking at the dissociation constants, so like Ka of strong acids, we said, you know, hydrochloric acid, the Ka is 1,000,000, right? That means out of 1,000,000 reactions, or 1,000,001, 1,000,000 are products and 1 are reactants. So it's a very heavily product favored. We're going to operate under the same principles, looking at neutralization reactions. So when I show HCl plus NaOH with a single unidirectional arrow, that's saying it's a very, very heavily favoring my products, and I'll form water and sodium chloride. And generally, when we're talking about neutralization reactions, the products are almost always water and some kind of salt, right? And salt typically means any ionic compound that was made by a neutralization reaction, so it's kind of circular logic. But it is an ionic compound created by neutralizing a strong acid and a strong base. So I realized there used to be animation on this slide. It looks like I got rid of them. That's why the arrows are all over the place. I apologize for that. But what I do want to do with this example is to actually do it a little bit slower. So the way I usually go through these slides in lecture, a lot of this is done on the board. So I'm going to do my best to do it, you know, via Zoom. So what I'm going to do is I'm going to pause on this slide. I'm going to move it to a Word document, and then we'll kind of use that as a whiteboard, and we'll do some work on that. And then we'll come back to this slide. So why don't we do that? I'm going to wipe that. Let me change my share to a blank Word document. If I can find, I don't know what, there we go. Sometimes the cursor just disappears. All right, so we have our blank document. So we had hydrochloric acid, and again, I'm gonna leave out states of matter. Like I said, you shouldn't be doing this. Well, actually, no, you know, if I'm gonna, you know, do as I say, do not as I do type thing, well, do as I do then. I'll put the states of matter in. So HCl, aqueous, is reacting with sodium hydroxide, aqueous. We said because we're recognizing it as a neutralization reaction, it's going to go approximately to 100% completion, and it will form water, liquid, and sodium chloride, aqueous. So there's 2 ways we can go about looking at these reactions. What I want to do is predict pH when the concentration of HCl equals exactly the concentration of sodium hydroxide. Technically, this component right here makes it neutralization. though in general, anytime you have an acid and a base react, we call it neutralization. The reason why this would be defined as neutralization is because you made water that doesn't affect the pH because it's neutral, and then you form a salt. The thing is, the salt is not always necessarily, it can and it cannot sometimes affect the pH. So we'll talk about that a little bit. So let's back up. It says predict the pH when hydrochloric acid equals the concentration of sodium hydroxide. So let's take a look. We don't need to do an ice table or anything like that fancy. I'm going to show you 2 ways to go about a problem like this. Number 1 is just to look at the molecular equation. With a little bit of foreshadowing, we'll look at the net ionic next. But if I was going to try to predict the pH here, I have pure water. So we know pure water, the pH is going to be 7, so it's not affecting the pH. It's going to be pH 7. And then I take a look at my salt, right? This is going to rely a little bit more on the end of chapter 16 when we were talking about salts that affect pH, right? Sodium, the Na+, came from a strong base. So therefore, it is a super weak conjugate acid. Chloride comes from a strong acid. So therefore, it is a super weak base. Effectively, the sodium and the chloride do not affect the pH to any substantial degree. So we're just going to say, make a reasonable assumption that it is not affecting the pH. So based on that assumption, so just using what we know from basically high school and the end of chapter 16, if these are my only things floating around in solution, my pH must be 7. So hopefully we all agree on that. So that's like the quick way of doing it, which I would probably always do if you're looking at strong acid, strong base neutralization. I'm going to show you a longer way to solve for this. And the reason why I'm showing you this is because we're going to use this longer way for the next 2 examples when we mix together like a weak acid and a strong base, or a strong acid and a weak base. So let me put our products back. Water and sodium chloride. So again, going all the way back to Gen Chem, we could call that the molecular equation because everything's written as a molecule, nothing's dissociated. If I went through and wrote the ionic equation, right, I asked myself, is this compound going to fully dissociate? Well, a strong acid will. We know that's going to dissociate into effectively H+, even though we know that doesn't actually exist as H+, right? It'll dissociate into chloride. Sodium hydroxide dissociates into sodium plus and hydroxide. We have our unidirectional arrow. Water is molecular, so it stays as water. And then sodium chloride is also a soluble salt, so we can break that up. And so in this case, I did leave out the states of matter because I feel like it's going to clutter up what I'm trying to show, but you would put your states of matter as well. Everything would be aqueous except for the water. And so if I take my last step and put in the net ionic equation, I need to go through and cancel out my spectator ions. So chloride is gone because it shows up on both sides. Sodium plus is gone because it shows up on both sides. And then I'm left with this net ionic equation of H plus in OH yields H2O. So we already see from this example, right, the only product that really is doing anything other than just floating around is water. And then we know that the pH of water is 7. I tried to make this a little bit more simplified, but if we did go through and actually follow, knowing where that proton actually goes, we know it's going to be hydronium, because that H would get picked up by some water molecule floating by. So a more appropriate way to actually would be to write it like this. I know we just made a little bit of a jump from ionic to net ionic, but like I showed you, we could still do it out with the H+. What I have written down here is just taking into account what's actually really happening. We know that H+ immediately finds a new water molecule and forms hydronium. So again, we have 2 different ways to do it. One, take a look at both the salt in the product, which is water, ask yourself, would that salt affect the pH? Nope, pH 7. Or go through the net ionic equation. The only product I have in that sense is water, pH is 7. So hopefully that felt like overkill and most people are going like, okay, I know that, move on, right? We're kind of setting the stage. That's the high school stuff. So what I want to move on to now is talking about, well, what happens when we switch it up a bit? Instead of having both being strong, what happens when one of them is weak, right? So I'm going to switch back to my slides. Right? And so we can see the same thing that I kind of slowly went through. Like I said, I'd usually do that on the whiteboard, but we get our summary slide effectively of talking about strong acid, strong base neutralization. Oops, let me change slides. Oops, yep, there we go. Now we're moving on to weak acid, weak base titration. So what I'm going to do, this is again more of a summary slide. So I'm letting us see what's going on. I'll highlight some key points, and then what we'll do is we're going to go through slowly again through like a Word document like I had prior. So I have my weak acid, acetic acid. I'm titrating it against or reacting it with the strong base sodium hydroxide, and then my two products are water and then the salt of the acid, which is my sodium acetate, right? Again, I said I'm gonna have to fix these as I go through. I usually probably wouldn't write that as an equilibrium arrow. The yes in real life, small amount goes backwards, but the majority of the reaction is heavily product favored. Why? Because it's a neutralization reaction and at least one of the components is strong. So we're gonna assume 100% goes to product. One way you could think about this, and I've seen other professors do this, is I've never really seen this term used before, but Kn for K neutralization, it's just going to be really, really big, right? So anytime you have a big K, it means product favored. So if you're talking about, you want to think in terms of Ks, you can just think that this is a very large Kn, so K neutralization. Another way to think about it. All right. So let's take this reaction. I'm going to move it over to Word, and then we'll pull it apart. All right. So let me write down, I'll recopy that reaction. We said we had acetic acid, so CH3. I usually write it like this, COOH rather than CO2H. So I'm going to write it like that. It's just left over from old slides. So I have my acetic acid, aqueous. I said I was titrating it with sodium hydroxide, aqueous. It's a neutralization with a strong base. 100% completion, I'll make the assumption. And then that's going to form water, liquid, and then I form my salt, which is always going to be the conjugate base. And then you have that sodium, and I'll draw them together, but it really would be the sodium still charged and the acetate still negatively charged, but you can write it like that. So all I did was really replace that H with the Na because I formed a carboxylate. We fixed that up, it looks pretty nasty. So it's COONA, right? And so that would be our molecular equation. Nothing really different than what I showed on the last slide. This one is going to make more sense if we slowly go through and then do our ionic equation and then look at the net ionic. So what I'm going to do for the ionic, and I have to, because I'm going to make an assumption and I have to tell you what it is. So I want to make sure that, you know, usually I'd have you walk me through it, right? I'm going to slowly go through this one because this is a new type of example. I'm going to skip over the weak acid first. I want to start with the sodium hydroxide. Sodium hydroxide is an ionic solid. Ionic solids that are soluble in water, 100% dissociate. Water's molecular, it's not going to dissociate. Sodium acetate is a salt. It will 100% dissociate. Right, and again, because I'm going to get a lot of stuff on the screen, I've omitted these states of matter for this example. So everything I wrote down right now, hopefully makes sense. What I've done, I've just asked the question, does it dissociate or does it not? And that's going back to Gen Chem 1. However, I have a weak acid. My weak acid is acetic acid. On a good day, which means low concentration, you're going to get about 4% dissociation. And it usually goes down from there. So you're talking about a very small dissociation. You know, we'll put 4 in parentheses because it changes. We can just call that, again, partial dissociation. Nowhere near 100%. So what I'm going to write it as then, instead as dissociating, I'm just going to say the majority of that molecule, let me get better spacing, is just going to remain as the protonated acid. That is our assumption, and it's a reasonable assumption because you're saying at most it's going to be like 4%. Usually it's a lot less than that. Again, that depends on the concentration. It changes the percent dissociation. But as long as we're on board with that, we're able to make the next step to go to our net ionic equation. And just like we did before, we cancel out anything that appears on both sides of the reaction. And so if I write down anything that doesn't cancel out, I see I have acetic acid reacting with hydroxide to form water, and then the conjugate base. So before I go to the next step, is there anything that needs to be clarified? Is there something that I maybe said too quickly or didn't explain well enough on why I approached this problem like I did? All right. So then I'm going to move on to the next question, which is predict the pH. I'm not asking for a number. I'm going to be asking, is it going to be above 7 or below 7? So predict the pH. Basically greater than 7 or less than 7 or equal to 7. Those would be our 3 options, right? Specifically when the concentration of acetic acid equals the concentration in this example of my strong base sodium hydroxide. So that's the question, just like what we did in the last example. So 2 ways I can look at it again, the quick way and then the longer way. Quick way tells me, well, if I have 100% formed products, I'm assuming that I think all of this is just gone. We're assuming because they're equal, they both get consumed, they're both gone. I have water and a salt. The Na is not going to affect the pH because it is the conjugate acid of a very strong base, which is NaOH. However, you still have this acetate floating around. So like I'm saying, doing out the net ionic equation, it's a little easier to see because it kind of cleans it up a bit. So if I'm saying I have equal amounts, I don't know, let's say it's 0.1 molar and 0.1 molar, right? We're saying it's going to 100% completion. So when the reaction is over, that means I'd have none of this left, none of this left. I really don't care about how much water I have, but I would have formed 0.1 molar of the acetate. I can go one step further. That means the only thing floating in maybe my beaker or whatever is just water and acetate. I need to be comfortable enough with my acid-base chemistry to recognize that the acetate will react in a second reaction. So everything up here is pretty much the first step. A second equilibrium is established where the acetate finds some surrounding water. The water behaves as an acid, donating an H to the acetate. It reforms my acetic acid, and in the process, creates hydroxide. If you create hydroxide, the pH will always be greater than 7. And that is going to be our rule. And I'll make a summary on a couple of slides. But our rules we've noticed right now is that anytime you have strong acid, strong base, if there's equal amounts, pH is 7. If I have a weak acid, strong base in equal amounts, the pH is always greater than 7. How much? I don't know, right? It's going to depend on how strong that weak acid is, or how strong that weak base is, right? So that's what I'm saying. We're keeping it generic. It's greater than 7 because I know I'm creating hydroxide, and we'll leave it at that. So how are we feeling on that? We were able to do a lot from this, right? But the take-home message was, could we predict what the pH would be when you have equal amounts of reactants? You feeling okay? All right. So what we'll do is, so if that wasn't feeling that great, and you're not asking questions, which is fine. I mean, we can always do it during office hours or some other time. Is we're going to get another shot at doing a similar reaction, because we're going to switch up what we're reacting. So in that last example, right, we did our weak acid, strong base. And so you still see, even though we did it out slowly, there's our net ionic equation, same one as I did on the Word document that I used as a whiteboard. Again, right, we want to make sure we're thinking about neutralizations with any strong reactant, base or acid. It's going to go almost 100% to completion. So once things have been neutralized, just like we predicted, the pH is greater than 7. So let's take our third example, right? Because we've done strong, strong, weak, strong. Now let's do strong, weak, right? So we'll take the example of having HCl reacting with ammonia. And so again, let's switch back over to the Word document, and then we'll attack this problem. This one's a little bit easier. So if I took my HCl and I react that with ammonia, again, right, one of them is strong. This time it's the acid. Last time it was the base. That means the acid is going to donate its proton to the base. So I'm left with chloride and ammonium. So what we see right off the bat, again, this one's a little easier. We could go through the entire, actually, well, we can do it really quick. Why don't we keep it consistent? Molecular equation, ionic equation, right? We know HCl is going to fully dissociate because it's a strong acid. Ammonia is not an acid, it's a weak base. They're not dissociating. Nitrogen, the reason why ammonia, right, and we discussed this at the end of chapter 16, right? We have that spot on nitrogen that's going to act as a Lewis base that's going to accept the proton, so it's not dissociating. So nothing happens with ammonia. And then I'm still left with, Cl minus plus NH4 plus. Right, so when I take a look at this, actually there's nothing to cancel out, right? We actually have a net ionic equation, or almost, sorry, my bad, I'm skipping ahead, right? We have our ionic equation, then we get our net ionic equation, jumping ahead, right? I see again, I have my H plus aqueous plus my ammonia, should be an aqueous up there, and it yields ammonium. If we wanted to be, we have to go in here and kind of make our own fixes, but we know a proton doesn't exist free in solution. So a more appropriate way to actually write this would be hydronium reacting with that ammonia. And so therefore it forms ammonium in water because that hydronium is losing an H. and we're in good shape. We just kind of, you know, had to modify it just a little bit based on reality, because we know H plus technically doesn't exist free in solution. And again, we can ask ourselves the same question. What's the pH going to be, right, if we have the equal amounts of HCl and ammonia? So that means I'm only going to be forming products, right? I can go through just from the molecular equation and say, okay, do I remember chapter 16? Chloride comes from this strong, very strong acid, HCl, so therefore it's a very weak base, effectively not affecting the pH. But ammonium is a weak acid, right? There's a difference between very weak, which is like basically not an acid or a base, and weak, because weak still has an effect on pH. It just happens to not be as strong as a strong acid. So the chloride doesn't affect the pH, the ammonium does. If we don't feel comfortable with that, we can go look at the net ionic equation, because it's telling you the chloride's just floating around. The only thing I have in solution is ammonium and water. Again, we have to think of this as a two-part step. The first part is the neutralization, and then the second step is recognizing, all right, what is floating around in my beaker? Ammonium and water. Well, if I get comfortable with my acid-base chemistry, well, I know ammonium's a weak acid. It will set up a new equilibrium with the surrounding water in the solution. The water acts as a base in this case, so it's going to accept that proton from the ammonium. It reforms ammonia, and in the process forms hydronium. Hydronium, right? Anytime we produce hydronium, the pH goes down, right? That means my acidity went up. And so again, we can predict that anytime I have a weak base titrated with a strong acid, my pH is going to be less than 7. Upon neutralization, that is, right? pH less than 7 when you have equal amounts of HCl and ammonia, or equal amounts of a strong acid and a weak base. So that was a lot, right? I want to give you a summary of the 3 we've just attacked. So before I wipe the page clean, any other questions that we want to talk about? All right, so let me summarize what we just said. So we looked at strong acid, strong base, right? I'll say at neutralization point. Basically, effectively saying when the strong acid equals the same amount as the strong base, right? We know pH equals 7. If we took our, what was it, a weak acid we did next with a strong base, right? We said our pH was going to be greater than 7 once everything's been neutralized. Why? Because that conjugate base has been made. Our example was acetate. Acetate reacts with the surrounding water, creates hydroxide. Hydroxide raises the pH. And then the last example we did was strong acid, weak base. And when we have equal amounts, right, we just showed ourselves that the pH will be less than 7 when it's been neutralized. Why? Again, right, this is the critical thinking part of this. It's not tough, it's just keeping track of where I'm going, right? I reacted all of my HCl with all of my ammonia. That produced ammonium. Ammonium then sets up a second reaction that interacts with the water to produce hydronium. More hydronium lowers the pH, making it more acidic. So it does take a lot of critical thinking. There's not just like, here's the answer. I mean, you could just memorize it, but I find that more difficult, honestly. It's easier to get an intuitive understanding, I think. All right, so you might have noticed that there's 4 combinations: weak acid, weak base, right? We do not cover that in Gen Chem. That becomes a lot more convoluted, a lot more difficult, in the sense that you need to really take into account how strong is that weak acid compared to the Kb of that weak base. And it becomes a little bit more involved. So for us, we are only going to stick to the first 3 that I did: strong acid, strong base; weak acid, strong base; strong acid, weak base. So hopefully we're on board with that. All set? All right, we're going a little bit slower than my last class, which is fine. what it will help us do is hopefully that will settle in well. And then what we can do is maybe go a little bit, not quicker, but we'll see where we get to. I'm not in a rush to get this done. Not, you know, we need to get done, but we're in a good spot. Let me stop sharing. Get back to the slides, and then we'll keep moving forward. And so again, this is our summary slide of everything that I just had. Not the last thing I wrote, but you know, talking about strong acid, weak base. There we go. So again, on this one, right, we could do weak acid, weak base, but we're not going to deal with that one. This leads us into talking about titrations. So I'm going to give you a definition first. This is the book definition. It makes sense to me, but I realize that it's a little bit ambiguous, and so I think we're really going to get a better sense when we go through the next couple of examples. So like I said, if you're not feeling that comfortable with it, that's okay for now. I think we'll get a better sense of it in the next couple of slides. So let's read through it to get our definition, and then we'll move on to talking about titrations. So it's a procedure for determining the concentration of a solution by allowing a carefully measured volume to react with a solution of another substance whose concentration is known. It's a lot of words. Basically, it's saying I have a solution. So there's a reaction, say it's an acid and base. Maybe I have a base solution where I don't know the concentration is, but I do know what the concentration of the acid is. And I can set up an experiment that actually will tell me the concentration of that unknown base. So like I said, we'll see it more when in the next example. It's kind of hard to show by words. One other definition we need to know is going to be the equivalence point. So it's going to be the point at which stoichiometrically equivalent quantities, so it just means the same amount, fancy way to say same amount, of acid and base have been mixed together. So everything that we did up until now, when I kept saying predict the pH, when we have exactly the same amount of an acid and a base, that technically is the equivalence point. So we get a new definition, but we've actually been using it the entire time. So what does a titration curve look like? And titration, the way we use it in this class, only refers to acids and bases. But it's just a standard term. I mean, I've done it with proteins and ligands, or you can do it with metals and a chelate or something like that. It doesn't have to be pH based. This is more of an introduction to the concept of titrations. And so we will only focus on pH curves. So what does the experiment generally look like? Well, what we usually have would be some sort of unknown solution. Maybe it's a base, maybe it's an acid. In this case, it's looking like it's a base, given that the pH is about 12 or 11.5, right? I have a known amount of an acid that I can then slowly drip in. And as I slowly drip that in, the reaction is going to happen and the pH is going to start to change. And when I graph that, I get this F-shaped curve that you're seeing over here. And I realized the way it's kind of done is like that number doesn't really agree with the two figures I chose. The idea is the same, right? If I started with an acid, so a low pH, and I add in a known amount of NaOH, I can start to track that neutralization reaction as it's going through to the point where the amount of NaOH equals the amount of the acid. Hey, look, it's exactly what we predicted. It's 7. All the acid's gone, so then I just keep adding more and more sodium hydroxide, and I just made it basic. That was the bird's eye view of this. We're gonna go slower, and I think we're probably only have a chance to maybe get through 1 or 2 of these, so we'll be a couple slides behind my last class, but that's fine. I think we're making good progress today. So what we'll do is we'll start out with each of those 3 types of reactions. So we'll start with strong acid, strong base. Then we'll do, weak acid, strong base, and then we'll flip it around. It'll be weak base, strong acid. So I have written down is our net ionic equation, hydronium plus hydroxide. It's a neutralization reaction where one of them is strong. Both in this case goes to 100% completion to form water. All right, so my iPad's getting a little laggy, so hopefully this works. My last 2 classes ago, I had a problem with it, so hopefully it's not acting up again. So if we go slowly through this, right, I'm going to just say, I'm arbitrarily picking. You could pick one way or the other. I'm just going to say I'm starting with an acid, and I'm going to titrate in a strong base. I ask myself, does this shape make sense right now? And it should. If there's no sodium hydroxide around, excuse me, there is only acid. There's a 0.1 molar solution of HCl, negative log of that number, you're going to get 1. Well, there you are. That makes sense. We've already predicted that. If we look at our reaction, right? Oops, I'm writing it backwards. We said HCl plus NaOH yields NaCl plus water, right? When I first start this reaction, there's no NaOH, but I start to slowly add a small amount. That means some of the HCl, not all of it, is being converted to sodium chloride and water. So I'm going to make up some arbitrary numbers. They don't really mean anything. Imagine I have like 100 HCls. I don't know, right? And then I only titrate on a small amount. Maybe it's 10 get titrated in. Well, if I let that reaction happen, it's going to go to completion until I run out of my limiting reagent, which would be sodium hydroxide. That means 10 of those 100 NaCls were taken away through the reaction. So there's only 90 left, right? I'm making these numbers up. They don't mean anything, and they don't go with the graph. It's more of a visual, quantitative explanation, right? And so I could do the same thing again. I could add a new, open up the stopcock, add a little bit more in, right? And titrated more in. Well, now I'll take an additional 10 away. And so the sodium hydroxide completely gets consumed because it's the limiting reagent. And now I'm left with a little bit less HCl, right? So we're slowly bringing that concentration down. And as we do it, we could follow that with the pH equation, right? Negative log of the concentration. And we'd start to see that the pH is just starting to go up. And that's what you'd expect. As soon as we get really close to having the same amount, imagine, we started again with 100 and then I titrated in 100, right? That means everything is consumed. The only thing floating around at that point will be sodium chloride and water. And we said that's not going to affect the pH, and we already rationalized that. And it's exactly what we predict. It's at pH 7. This reaction is effectively over now because there's no more HCl. This next drop of NaOH does nothing except increase the pH. And that's why you see a massive, quick increase in the pH where it looks actually almost vertical, right? So what you do is you start adding more more and more NaOH, and all it's doing now is just making the solution more and more basic. There's no reaction anymore because the only thing floating around is salt and water. Yeah, the NaOH technically reacts with water, but that just falls apart. The NaOH just dissociates into OH minus. That's why my pH is going up. So let me walk you through a little bit slower. That was kind of like the bird's eye view. I'm just going to go slowly through each slide. The same thing, but you'll see what I'm talking about. Right, we start with HCl. I add a little bit more NaOH. I still have excess hydronium or excess HCl. That's why the pH is still below 7. At some point, the amount of HCl and NaOH, or you could write it out as the net ionic equation, is hydronium and hydroxide. They're equivalent. So we already went over that in the beginning of lecture, pH 7. Sorry, it's the same graph. I just ran out of space, so I had to shift it to the left-hand side. My apologies, but right. And like I said, you start adding more NaOH past the equivalence point, there's no more acid. All it does is rapidly make the solution more basic. All right, what I want to do, we have 5 more minutes. We'll probably only get through this last titration. And then what we can do is on Wednesday, we'll pick up with the strong acid, weak base. It'll be almost identical to this, except it'll look like a mirror image. And maybe that will be a good way that we can kind of get our feet back into things on Wednesday, kind of refresh our minds. So I'm totally fine with that. We'll just be literally behind by like 2 slides. All right. So in the last 5 minutes, let's compare. I have actually 2 graphs, two experiments superimposed on the same graph. I'll talk about that in a second. But let's take stock of where we are. There's my acetic acid reacting with my strong base sodium hydroxide, right? We said the products are water and then the weak base acetate. And again, I had to go through and fix those slides, right? This is a titration. Strong base tells me it's going to be pretty much unidirectional. We can go through the same questions we started with. So again, I can start with that weak acid. Again, let's take a look at when there's no sodium hydroxide. So the red line is actually the titration we just saw in the previous couple of slides. So that's my strong acid, strong base titration. The blue line right here, right, is talking about the weak acid, strong base titration. And immediately we can see things are different. Why? Well, it makes sense. They're both at the same concentration. I know it's kind of fast to read. It's the same amount, same concentration of acid, but it makes sense that the stronger acid has a lower pH than the weaker acid, right? So it makes sense to start at a different point. The difference here, we see the shape is different for a weak acid, strong base titration. So let's explore that, right? We follow the same ideas. We're adding small amounts of sodium hydroxide, so more and more of the acetic acid is being pulled over to water and acetate. At a certain point though, right, let's make up some arbitrary numbers. Again, I'll say I'll start with 100 of this and 50 of that, right? I'm just making it up. When the reaction is complete, my limiting reagent runs out. That means half or 50 of my acetate must remain. Well, it means 50 reactions went forward, right? Therefore, I would have made 50 acetate. Also 50 water, but I don't care about that, right? So when things are all said and done, once that titration's over, I now have a 1-to-1 molar ratio of a weak acid and its conjugate base. That, by definition, is a buffer, right? When you need that weak acid with its conjugate base, if they're in sufficient amounts, they form a buffer. That's what you're seeing here at this shaded region. That is the buffering region. Specifically, right, you see a point where it says pH equals pKa. And so if you've already watched the YouTube video, you'll see I did an exact example of that, kind of foreshadowing. We know from the Henderson-Hasselbalch equation that pH equals pKa plus the log of the concentration of the conjugate base, sorry if you hear the recycling outside, right, over the conjugate acid. When they're in a 1-to-1 molar ratio, like I have here, 50 and 50, right, 50 divided by 50 is 1. The log of 1 is 0. What that's telling me is when the amount of sodium hydroxide, the amount of acetic acid and the amount of acetate are equal, I've actually hit the buffering region. And buffers are pretty much only effective plus or minus 1 pH unit away from the Ka, and that's actually what you see here. The buffering region is pretty small. The idea is you have to have a good amount of the acid and a good amount of the conjugate base to really form a buffer. When we're on the low end over here, right, there's still a lot of acetic acid, not a lot of acetate, not very good buffer. But as we move into the middle region, we have equal amounts. That's a good buffer. And as I start to move further from that, right, things are starting to switch more heavily from the acetic acid to the acetate side, and it's called breaking the buffer. And so that's why you see all of a sudden, we had this really gradual change in pH, because that's what buffers do. They resist changes in pH. And then all of a sudden, once the buffer's broken, I add a little bit of sodium hydroxide. Oops. What's it doing? There we go. And I get this jump up rapidly because I've broken my buffer. It follows our prediction. We said, well, once all of the acetic acid has been used up, the only thing floating around in solution is water and acetate. Acetate interacts with water, forms hydroxide. pH should be greater than 7 at the equivalence point. Exactly what we see. It's pH 8.7. And we've already predicted that without even knowing what titrations were. After that, it follows exactly what happens with strong acid, strong base. There's literally no more acid around. You add a drop of sodium hydroxide in, it just shoots up, and the pH just becomes more and more basic. All right, so we're exactly at 1150, and I think we did actually a really good job. We're just a little bit slow, and I think that's fine. I think as long as it makes more sense, I'm fine to go a little bit slower, as long as we get everything done. All right, so if you have no questions, free to go, head out. If you have any questions, I can stick around for a little bit. And I'm going to stop the recording now.